Hey everyone, today we're looking at notes Kk-1, Rationals Day 1. So just a quick review of the rational parent function that we learned in Algebra 2 and further investigated in pre-cal. Y equals 1 over x, so that's your rational parent function. So keyword there, function, right? So our rational graphs that we're going to be working with are functions. Okay, we took that rational graph and we did things such as reflecting it. So you might have seen the curves switch quadrants. They were no longer in quadrants 1 and quadrants 3. When you reflected, the curves were in quadrants 2 and 4. We haven't quite worked with this, but this is a new parent function. We are going to be working with lots of different types of rational graphs now. So this is just one example. Something like y equals 1 over x squared, where now both curves are above the x-axis. And I bet if you kind of think of it intuitively, it kind of makes sense, because if you're squaring the denominator, any number squared is going to produce a positive value, so of course you'll never have any negative inputs. So that's another example of a rational function that we'll be working with. We're going to work with many different shapes, but basically what you need to understand is that all we are working with is functions. We are not going to be working with non-functions, nothing like this kind of shape where it doesn't pass the vertical line test. If I were to take a vertical line and pass it through the graph, of course I'd hit 2 points at once, and so this graph does not pass the vertical line test. It is not a function. We won't be working with anything like that. So that's good news, because when we go to graph these functions, knowing that they are functions will help. It'll kind of help us see where our curves go. You'll see what I mean here in a little, and in the further lessons like Kk2 and Kk3, etc. Alrighty, so for sake of time, I've already filled this in. So wholes are where factors cancel. I don't really like that word, but I think in this case cancel is probably better than simplify. So wholes is where factors cancel. Intercepts are going to be written as ordered pairs. We're going to be finding both x and y intercepts today. Okay, to find an intercept, set the other variable equal to 0. So finding an x-intercept, set y equal to 0. Finding a y-intercept, set x equal to 0. Okay, state an intercept as a point, coordinate, or OP, which stands for ordered pair. Okay, the x-intercepts are also called roots, zeros, or solutions. So just look out for those other vocabulary words, okay? Because they might not always say x-intercepts. All right, a VA stands for a vertical asymptote, and those would be written as x equals. It's where you will set the denominator equal to 0 and then solve, because remember, you can't have 0 in the denominator. If you type in divide by 0 in the calculator, you'll get an error, right? So that creates a vertical asymptote when you do have a factor that produces 0 in the denominator. Basically, it creates a space where you can't use that x value, because that would produce an error type situation, an undefined situation. We'll kind of describe that further soon. Okay, HA stands for horizontal asymptote, and you will write your answers for HAs in the y equals form. You will look at the degrees, which are the highest exponent on the variable, of f of x divided by g of x. So the rational function, you'll look at the degrees in the numerator, you look at the degrees in the denominator, and you will compare them. And so I have kind of a method for that. So if f of x, if the degrees of f of x are less than the degrees of g of x, then y equals 0. We have a little acronym for that. We say BOB-YO. It stands for bigger on bottom. Y equals 0 is your HA. So bigger on bottom means the degrees on bottom are bigger. Notice bigger because the alligator mouth is eating the bottom, okay, the g of x, okay? So if your degrees on bottom are bigger, you have a horizontal asymptote that is y equals 0. If the degrees in the numerator are bigger than the denominator, then there's no horizontal asymptote. That's why we use the acronym BOT-NO. Bigger on top, no horizontal asymptote. Okay, we're definitely going to talk about this more later, because while there's going to be no horizontal asymptotes for those graphs, there will be what's called an oblique asymptote. It's like a slanted asymptote, and we'll come back to that later. We're just not ready to get into that just yet. Okay, and then last but not least, There's only one other condition. So either bigger on top, bigger on bottom. Well, really I said bigger on bottom first. Bigger on bottom, bigger on top, or are your exponents are the same. So are the degrees the same in the numerator and denominator? If they are, then your HA will equal the lead coefficients. You will basically divide the lead coefficients, okay? So, and what this stands for right here is exponents are the same, divide coefficients, okay, of the terms with the highest degree. And we'll talk about that. I have examples right here. So we're not going to get to the two graph yet. So right here are just examples of using the Bob-Yo, Botno, Eats DC, the acronyms, to find the HA, to find the horizontal asymptote. So for example, this is a rational equation. It's a rational graph. It's an interesting one, but it is a rational function. So if you're given a rational function like this and you're asked what is the HA, what is the horizontal asymptote, you're going to look for the term with the highest exponent on the variable, which in this case would be this term. In the denominator, it would be this term, the lead term. If they've been nice to you, then it'll be in the front. Sometimes they scramble the terms, so you never know. You got to be careful. And then you examine the exponent. What is the highest exponent here in the numerator? Well, it's 2. The highest exponent in the denominator is also 2. So that is a exponents are the same situation. So remember, these are your three scenarios. So if both of my degrees in the numerator and the denominator are 2, then exponents are the same, divide coefficients. So the coefficient on this term is 3, the coefficient on this term is 4, so 3 divided by 4. So your HA would be y equals 3/4. Okay, in this problem situation, you analyze what is the term with my variable that has the highest exponent. That would be x to the first here. Okay, and then on the bottom, this would be x squared here. So my degree in the numerator is 1, my degree in the denominator is 2. That means I have a bigger on bottom situation. 2 is definitely larger than 1. So bigger on bottom means y equals 0. So my HA for this rational function would be y equals 0. And last case scenario, examine your degrees. My degree in the numerator is 3. My degree in the denominator is 1. I'm obviously bigger on top because 3 is bigger than 1. So bigger on top, there are no HAs. So you would answer that none. Okay, so we're going to get started. We're going to follow these directions to graph these rational graphs that are going to be very interesting from anything we've done before. You will graph all the key features found. Then we will maybe possibly have to plug in a few extra points where needed. Okay, so pause the video if you need to copy anything down. You haven't gotten everything yet. I'm moving on. Okay, next page. Page 2. I filled a little bit of this out, but not too much. Okay. So number 1, here's our rational function. We are going to graph this guy. Okay, what was given to us in this case, it won't always be the case, but in this case, this is called the unfactored version of this equation. As you can see, we're not factored in the denominator. Of course, the numerator is just a single term, so we're not really looking at that, but in the denominator, we are unfactored. So I went ahead and, just like you will want to do, I went ahead and factored the denominator. I looked for numbers that multiplied to 9 and added to 6, which was 3 and 3. And since the a value was 1, I didn't have to do factor by grouping or anything fun. Okay, I just got to use the numbers from my table, so 3 and 3. This is now called my factored version. Whenever we find key features, we will be looking at certain versions. So when we're looking for the roots, we'll use the factored version, the VA factored version, HA unfactored version, and then for the y-intercept, you can use either. I'm sorry this pen is kind of light, but hopefully you're getting it. Okay, so just so you're aware, and I'll kind of talk you through that as we go. So I already got this one kind of set up. So roots, remember roots is just another vocabulary word for x-intercepts. So remember, when you find intercepts, you set the other variable equal to 0. So if I want the x-intercept, I'm going to set y equal to 0. Okay, so let's just get to it there. So I have my equations, and probably best in this case to use the factored version. And you'll see why probably in the, oh, well, not really in the next one, but you'll see why on the assignment. Okay, but this one ends up being not too bad because the numerator is just a single term. But we're going to take the factored version, and we're going to plug in 0 where we see y. So we're going to have 0 equals 3 over x plus 3, x plus 3. Okay, and what do we do here? Well, easiest case scenario is probably just to put the 0 over 1 and cross multiply. Okay, so 0 times the denominator here equals 1 times the numerator here. So 0 times x plus 3 times x plus 3 is equal to 0. Okay, and then 1 times 3 equals 3. Does 0 equal 3? No, that's not even a true statement. So in this weird scenario, this unique scenario, we have a situation where when we set y equal to 0, we got an untrue statement. So that tells us that there are no roots. So the answer for roots in this case is none. Okay, so hopefully you can kind of see that what's going to happen every time you plug in 0 for y in a rational graph, since you're dealing with a fraction like this and you've got 0 over 1 and then you cross multiply, the denominator is always just going to turn to 0. So it's always just going to be that you're really just setting the numerator equal to 0. The roots or x-intercepts come from, that's why I have this other arrow here, just setting the numerator equal to 0. So kind of like a key step there. I mean, you could always just do it the way we did it here. It's just I'm trying to save you a step because it's a pattern. You see what I mean? So just trying to kind of save you a step there. So for the VA, remember the VA is going to come from where the denominator equals 0. And remember, that's because we talked about this before. I think it was like E2 kind of, whenever we discussed the domain of equations analytically, like with algebra, we would set factors in the denominator not equal to 0. Okay, and we just knew that those values weren't in the domain. Any values that when you plug them in to the denominator would produce 0 in the denominator. Okay, we never really specified that those were VAs, but you can probably see now that they would be. Okay, so denominator equal to 0, and we're in the factored version. So you would typically set both factors equal to 0 to find the VA, but in this case, since both factors are exactly the same, there's no reason to do it twice. So x plus 3 equals 0, so then x equals -3. So your VA, your vertical asymptote, is at x equals -3. Okay, so then next HA. HA, remember, is our little acronyms. So you want to look at your unfactored version because it's really hard to see the degree here because you're factored. So it's really easier to see the degree in the unfactored version. So based on this unfactored version, look at the numerator. There's not even an x. So your degree in the numerator is 0, okay? Because you could put an x to the 0 there, which is the same as just like multiplying 3 by 1. So essentially no variable in the numerator means your degree in the numerator is 0. My degree in the denominator is 2. 2 is definitely larger than 0. So I am bigger on bottom. Okay, so remember, it's degrees. That's how you find the HA. You examine the degrees. Okay, and in this case, we have a Bob-Yo situation. We are bigger on bottom. So y equals 0, bigger on bottom, degree. So y equals 0 is our HA. Okay, last but not least, y-intercept. Remember, y-intercepts are where you plug the you plug in 0 for the other variable. Sorry, I'm trying to do two things at once. So that's where you set x equal to 0 to solve for the y-intercept. So you really have a choice. It's kind of like, what do you like to work with? Do you want to plug in 0 here, and then do like 0 plus 3 is 3, 0 plus 3 is 3, and then multiply those, and then just kind of finish off this fraction? Me personally, I usually go for the unfactored version. I'm going to this time. Just because typically then when you're plugging in 0 for x, look at what happens, 0, 0. Like everything basically goes to 0. So, and usually how I show this one is by writing, you're evaluating the function, well, okay, so it's not really f. So I'd say you're evaluating y at 0. So y of 0, basically this is just saying I'm plugging in 0 for x into the equation for y. So that is 3 over 0 plus 0 plus 9. Agreed? That would be 0, that would be 0, and that's 9. So then just clean it up. It's 3/9. Clean it up a little bit more. It's 1/3. So remember to write your answers like from the front page as an ordered pair. So your answer would be 0, 1/3. Okay, so now let's put it all together like it said in the front. So graph all the key features, then determine if we need extra points. I'm going to use pencil just to be safe for this, okay? So let's see. We have no roots, okay? So there's nothing to graph there. I have a VA, a vertical asymptote at x equals -3. So 1, 2, 3, and I'm going to draw a VA. Okay, I've got a HA at y equals 0, so just to make sure the reader can see it, I'm going to kind of shade it a little darker. Okay, horizontal asymptote at y equals 0, just kind of make sure you can see it coming off the graph, or make sure you can just see it. Okay, and then my y-intercept is at 1/3. So if this is 1, then 1/3 would maybe be like right here. Okay, so let's talk, y'all. I have no other information. Okay, all I know is that I have to have a function. So to the left of my VA, I can only have one curve. I can either have one here or here. I have no way to tell unless I give an extra point. So for sure, I'm gonna have to do an extra point to the left of to the left of my VA. Okay, so what would be the first, probably the easiest value to plug in, the first value that's to the left of my VA? That'd be -1, -2, -3, -4. So I'm going to evaluate y of -4. Okay, so y of -4, and probably, again, it's kind of your choice. In this case, maybe let's go for the factored version. That might be easier. So let's do 3 over, and then -4 plus 3. I'm plugging into the original equation, and then -4 plus 3. Okay, so that's going to be 3 over -1 times -1, which is +1, so it's going to be 3. So my extra point is -4, comma 3. So -1, 2, 3, 4, +1, 2, 3. So about there. That tells me, y'all, that tells me that my curve has to be up top and not down low. So then I just need to draw a curve that kind of hugs the asymptote. I really don't care if you find more extra points. If you're a little OCD, you kind of want to figure out, you're inquisitive, you're curious, you want to figure out what's going on, then by all means, go for it. But for me personally, I only need one so we can see where the curve goes, either up or down. Okay, so we've got our curve. Make sure that it looks like it's hugging the asymptotes, being pulled to the asymptotes like a magnet. Okay, make sure it doesn't look like it starts to go out or anything crazy. It should get closer. It'll always only just get closer and closer to the asymptote. Okay, now on this side, it's easy. On this side, I don't need an extra point because I've got a point here. I've got a point here, so that means I can't have a graph down here, because if I had a graph down here, I'd have a y-intercept down here, and I wouldn't have one up here, and it wouldn't be a function if I had both. So this point here saves me and tells me, oh, my curve on this side to the right of my VA must be up. And then again, make sure your curve just looks like it's hugging and being pulled to the asymptotes. Okay, so this is already a long video, so I'm gonna try and go through this next one pretty fast. All right, number 2. I've already factored the numerator and the denominator, and I want you to see something. So hopefully you can clearly see the factors of x plus 7 cancel. Okay, so that was on the front page, remember? So then we're left with y equals x plus 3 over x plus 5. That means, if you remember from the front, that you then have a whole at x equals -7. And I got -7 because if I set x plus 7 equal to 0 and solve, then I would get x equals -7. Okay, and that's great to find the x value, but you need to find the point. Where is the ordered pair? So we're going to go ahead and find out what y of -7 is. And when you do that, you don't go back to the original. So just be aware now, this is all we can work with. Once you have a factor that cancels, so we're going to go ahead and write a note to ourselves. Don't go back to original equation when there are holes, except, the only exception is, except to plug in y equals of calc. Okay, otherwise we won't go back. So this will be both our unfactored version, because you can't factor this any further, okay, and it's factored. Okay, so it kind of becomes both in this case. Alrighty, so whole at x equals -7, let's find the y value. So we don't go back to the original anymore, we're done with him, unless we want to graph in the y equals of the calc. So let's go ahead and plug in -7 in the numerator, that'd be -4, over -7 in the denominator would be -2, so that would produce +2. So the whole is at the ordered pair, -7, 2. So maybe somehow make a note of that. Make sure you don't forget that. So I'm going to kind of just circle it to know that we need to come back to that. Okay, so remember, roots comes from where the numerator is equal to 0. The VA comes from where the denominator equals 0. The HA comes from looking at the degrees. And the x-intercept is where you plug in 0 for x. Okay, let's go to town. So, remember, we don't go back to the original. We're only going to this guy. Numerator equal to 0. So x plus 3 equals 0. We would get x equals -3, but it's a root, it's an x-intercept, so write it as an ordered pair. Okay, denominator equal to 0, x plus 5 equals 0. So x equals -5 for that guy. Degrees, what do we have? We have an eats DC. Exponents are eats DC. Exponents are the same. We have x to the first, divide coefficients. What's the coefficient on this x? 1. What's the coefficient on that x? 1. 1 divided by 1 is 1. So there's my HA. Plug in 0 where I see x. So essentially calculate y of 0. So that would be 0 plus 3 over 0 plus 5, which would be 3/5. And remember, write that as an ordered pair, 0, 3/5. Okay, so a little bit more than half, I guess. Okay, so let's go to town graphing so we can finish this up for you. Roots, -3, 0. 1, 2, 3. VA, -5. Oh man, 4, 5. Okay, I didn't do it tiny enough. I'm sorry. Okay, so I'm gonna have to kind of extend this. -1, 2, 3, 4, that's 5. So I'm just gonna have to do one more, -6. Okay, and then that's not a, I don't want you to think that's a root. It's just my line, it just kind of got dark. Okay, this is the only root. -5 is my VA. HA is at 1, y equals 1. So go ahead and draw that in. Okay, and then my y-intercept is at 0.3 So this is 1. It's got to be a little bit like maybe there-ish. Okay, so on this side to the right of the VA, we know our curve is down low because we've got points. So if we've got points down there, we've got to have the curve there. On this side, we need, oh, hold on, wait. No need for extra point. Why? Why do I not need an extra point? If this piece to the left of the VA was below, if it was below the HA, the horizontal asymptote, we would have to cross through the x-axis at some point. There's no possible way to have a curve down here unless it were to pass through the x-axis. And do we have any more roots? No, we don't. So the curve must go up here. We don't need an extra point to know that. Okay, must go up, not down. So I know my graphs are a little sloppy. I'm sorry, I was trying to go quick for you, but hopefully you kind of caught the gist, and we can practice more in class tomorrow. See you soon.